Welcome. So in this video we will learn about the concept of zeta potential and how to determine zeta potential by laser Doppler electrophoresis that we will understand in this video. Okay, let us first understand the concept of zeta potential from the figures on the slide. So in simple terms, zeta potential may be defined as the charge on a colloidal particle in a liquid solution. That is mean to say this is a negatively charged particle. This particle is negative charge, so some positive sign by electrostatic interaction this will be adhering to this negative charge particle, and this will be tightly bound to the negatively charged particle, and this layer is known as the stern layer. And we can see that around this layer there is another layer where this positive, most of the positive and some of the negative charge also, they can freely move, and these are loosely arranged, and the ions are loosely arranged, and they can freely move in this layer. So this layer is known as the diffuse layer, as it is written here. So this is diffuse layer, this is stern layer. Thus there is formation of double layer around the particle. One layer is known as the stern layer, other layer is known as the diffuse layer. So this plane, there is this boundary which is there between this stern layer and the double layer is known as the sleeping plane. So this boundary is known as the sleeping plane, and we are actually measuring the zeta potential, or the potential at the sleeping plane itself is called as the zeta potential. So potential at the sleeping plane is called as the zeta potential. Now if we see this graph, we have graph this here, the graph between millivolt and the distance from the particle surface is shown. So as the particle's distance is increasing from the particle surface, the zeta potential is decreasing. This is indicated from this graph. So it is obvious that as the distance from this particle will increase, the zeta potential will obviously will decrease. From this slide we can understand it. So again I'm repeating, zeta potential is charge on the surface of the particle in a liquid, and here if you see the concept that if you have a colloidal particle, it is having negative charge. So if some of the positive ions will be adhering strongly to this negative charge particle, and they form a layer, and that layer is known as the stern layer, and outside layer there is another layer which is called diffuse layer, because here ions can move freely and they are loosely arranged. So there is formation of double layer formation, and this boundary between the stern layer and the double layer, stern layer and the diffuse layer is known as the sleeping plane. And actually potential is the measurement at this sleeping point itself. So if you in a liquid, if you are measuring the zeta potential, that potential will be measured at the sleeping plane. That's the meaning. And this graph shows that the distance from the particle surface, as the distance from the particle surface increases, the zeta potential is decreases. That our zeta potential is obviously will decrease. Okay, so now let us see what is the basic principle of zeta potential measurement. To determine the zeta potential of any colloidal particles in a solution, we place the solution or the liquid in a cell as shown on the slide. That this is a special cell where we have positive electrode and the negative electrode. So here you see here it is positive electrode, here it is negative electrode, and as the particles are having charge, so they will be moving towards the opposite electrode. So positive charge ions will move toward the negative electrode, where negative charge ion will move toward the positive electrode, and their velocity will depend on the charge on their on the particles. More higher is the charge, so it's written here, higher is the charge, higher will be mobility. Lower is the charge, lower is the mobility. Say if this is positive electrode, this is negative electrode, we are applying voltage of V between these two electrodes. The distance between these two electrodes is D. Then electric field strength is given by P by D. This we know that if the voltage applied between the electrons is V and the distance between the electrons is D, then electric field strength is given by E. So from this E we can calculate the electrophoretic mobility. Electrophoretic mobility is given by the velocity divided by electric field strength. So if we could able to calculate the velocity, so that we'll see in the coming slide, how to determine the velocity of the particles when placed in electric field, that we will see in the coming slide. And then electric field seed, we have from this formula electric field strength will come, and then from this we can be able to determine the electrophoretic mobility. So this is electrophoretic. Electrophoretic mobility. Now from this electrophoretic mobility we can calculate the zeta potential by Henry equation. That also we will see in the coming slide. Okay, now let us see the concept of laser Doppler electrophoresis. Now let us see the concept of laser Doppler electrophoresis. So this is the design. Here we can see that the laser light is passed through the colloidal particles in a solution to which electric field is applied, and the scatter light is measured by a detector which is placed at 12.8 degree. Now this angle is selected based on the fact that this angle provides a balance of the sensitivity, accuracy, and practicality. So actually this angle can measure the small frequency shifts that happen because of the movement of the particle that happens because of the change in the frequency, and then this angle also avoids multiple scattering, and the intensity of the light, the scatter light, will be measured, that is reaching detector will be higher if the angle is 12.8 degree. Now see this figure. If the particle velocity is 0, then the scatter light frequency is same as the incident frequency of the light. So the f1 here is also f1. If the particle is not moving, then the frequency of the scatter light will be same as the frequency of the incident light. But if the particle is moving, that is velocity is greater than 0, then because of the Doppler effect, the frequency change will happen. So here it is f1 and here it is f2. So delta f, that is change in frequency, that is, or simple terms, frequency shift, can be calculated from this frequency shift equation. That the frequency shift will be determined by the instrument, and then velocity of the moving particle can be calculated from the frequency shift equation as shown on the slide. So the lambda is the laser wavelength, theta is the scattering angle, and the v, that particle velocity, can be calculated from the change in frequency that is measured by the detector. Okay, so once we will have the velocity, that particle velocity we will have, then we will able to know the electrophoretic mobility, which is given by u equal to velocity divided by electric field strength which is applied. Okay, and from this electrophoretic mobility, zeta potential can be calculated, that we will see in the coming slide. And if we see, finally the we have the electric phoretic mobility value with us. So this we have calculated in the previous slide. So from the velocity of the particle that is obtained, we will be able to calculate the electrophoretic mobility by this equation. So velocity divided by electric field strength is equal to the electrophoretic mobility, and the other constant value can be put in this equation. This is called as the Henry equation. This is epsilon is the dielectric constant for the medium. Zeta potential we have to calculate, that the instrument will calculate automatically from this equation, and then this is Henry function, that this neta is the viscosity, and if we put all these values, then we will able to know the zeta potential of the particles in the solution. Okay, so this equation I've already explained to you. So if this is an electrode and two electrodes are there, and this is the distance between the electrode and V, the voltage applied, then electric field strength is given by V by D. This we know. And then if the velocity, as we have taken in the previous slide, we have seen that the velocity is determined by the Doppler effect or laser Doppler electrophoresis that we have seen in the previous slide. That velocity can be put in this equation, and then we have electric field strength from this equation. So we will be able to know the electrophoretic mobility, and this electrophoretic mobility, from this electrophoretic mobility and other values like a dielectric constant, viscosity, Henry function, we will be able to calculate the zeta potential finally of the colloidal particles in the solution. तो इस तरह से हम जीटा पोटेंशियल किसी भी क्लोइडल पार्टिकल्स का सॉल्यूशन में हम निकालते हैं. बेसिक प्रिंसिपल इसका लेजर डोपलर इलेक्ट्रोफोरेसिस होता है. थैंक यू. Okay, now let us discuss the significance of the zeta potential, why we determine the zeta potential of the colloidal particles in a solution. Now it's written on the slide that zeta potential indicates the degree of electrostatic repulsion between the charged particles in a colloidal solution. So higher is the charge on the particles, there will be more repulsion, more stability of the particles will be there. Lower is the charge on the particles, there will be lower repulsion, and thus aggregation may happen, and indicating colloidal instability. So it's written that higher zeta potential means maybe it may be positive side or negative side. Particles will repel each other. This will be leading to the stable system, or there will be low aggregation tendency for the system. Now if we have low zeta potential, that is its value is ranging from close to 0, then repulsion is weak, then particle may aggregate or flocculate, causing instability, indicating instability of the colloidal particles. So it's written what is the recommended values for a high stability system, high stable colloidal system. The ideal values range from greater than 30 millivolt, and if less than minus 30 millivolt, then we will say that the system is of high stable or high stability system is there. That is, there will be strong electrostatic repulsion will be there between the particles that will prevent aggregation, resulting in stable colloidal system. Now if the zeta potential lies between 10 and minus 10 millivolt, then we will say that the system is highly unstable. There will be weak repulsion, leads to particle aggregation and flocculation. Now if the zeta potential between plus 10 to plus 30 millivolt or minus 10 millivolt to minus 30 millivolt, then we will say that there is moderate stability of the colloidal system. Some repulsion will exist, but particles may still aggregate over time. Okay, so this is why mostly we are determining the zeta potential of the colloidal solution to check the stability of the particles in it. How much time if the value or ideal value should be that it should be greater than plus 30 and less than minus 30 millivolt, then we will say that we have a higher stable system. And if the value ranges between minus 10 millivolt to 10 millivolt, then we'll say that it's highly unstable, because there will be weak repulsion and the particles will get aggregate or flocculate. So unstable system will be there. But if the zeta potential lies between plus 10 to plus 30 or minus 10 to minus 30, then we will say that we have a moderate stability, that some repulsion will exist, but particles may aggregate over time. Thank you.